Hello and welcome to Precalculus lesson number 37. In this lecture, we're going to look at an overview of conic sections. We have done plenty of graphing when it comes to conic sections. So in this lecture, we're going to be mostly interested in identifying conic sections from their equations, even without graphing them. As you recall, when you slice a double-napped cone, as shown here, with a plane, you end up with three types of non-degenerate conic sections depending on the angle of the cut, which we have discussed in detail previously. The three non-degenerate types are the ellipse, the parabola, or the hyperbola. Or you may end up with one of these degenerate conic sections, the point, the line, or a pair of intersecting lines. What we would like to do is learn how to identify which one of these conics we're dealing with by just analyzing the equation that's given to us. So far, we've studied the standard form of conic sections in quite a bit of detail, as you can see outlined here. I'm not going to go over all these line by line. I'll leave it here for you to look at. You can pause the video to refresh your mind regarding these different types of conics that we've studied in the past three lectures. First thing we're going to do is look at another form that we have encountered also, called the general form of conic sections. We know that the general form for conic sections is the form given here: ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, where these coefficients in capital letters are real numbers and x and y are real variables. When it comes to identifying the non-degenerate conics, a and c, which are the coefficients of the square terms, play the most important role. But the problem with the general form is that even if certain conditions are met, we cannot be guaranteed that we're going to have a certain kind of conic section. So the safest way to determine what conic is represented by a conic equation in general form is to put it in one of the standard forms that we've learned, and then we can tell for sure what kind of a conic we're looking at. But if we're going to try to guess what kind of a conic we're dealing with, these conditions would have to be met for sure. If a and c, which are the coefficients of the square terms, happen to be the same, there's a high probability that the conic will be a circle. And basically what we want to have is that they should not be 0 and they should be equal. Okay, now the equation may represent a non-circular ellipse if a and c have the same sign and different non-zero values. Okay, because if they have the same non-zero values, then they would be representing the equation would be representing a circle. So we want them to be different non-zero values. So a and c are not 0 and not equal. The conic equation in this form may be a parabola if a or c, but not both, are 0. So one of them has to be 0, but they can't both be 0. So then we have the possibility of a hyperbola if a and c have opposite signs and non-zero values. Okay, so this is the scenario for that. When it comes to degenerate conics, you definitely want to try to be in standard form, because they will be much harder to detect in general form. For the line, it's relatively easy, because if all the coefficients are 0 other than the ones with the first power of x and y and the constant, then you know we can recognize this as the general form of a line. So this should turn into a line, right? For the point, once you put the equation in standard form, you'll end up with one of these possibilities: either the elliptical form but with a 0 on the right, and it doesn't matter where the larger number in the denominator is, whether the a squared is under the x or the y. As long as we have this format with a 0 on the right, we should end up with a point. And the way these are basically two intersecting lines are known as a degenerate hyperbola. Basically, it's what happens when you slice the double napped cone with an angle of 0 relative to the vertex angle. So in other words, right parallel to it and at a 0 angle, and it also crosses the vertex. That's when you end up with your with your two intersecting lines. And basically, you're either going to have this format or this one, right? With quantity x minus h squared over a squared minus quantity y minus k squared over b squared equals 0, or quantity y minus k squared over a squared minus quantity x minus h squared over b squared equals 0. All right, now, and at other times, an equation in that general form may generate no graph at all. That's when you would end up with one of these two scenarios. Because notice here we have squares up here, which should be non-negative, and in fact usually non-zero as well. So this sum should never end up being negative, right? Either in this format or this format. So when they do, then you're not going to end up with any kind of a real graph. So that's how we know we get no graph at all. So let's go ahead and start identifying some conics. Now, with some of these, our knowledge of some of the simpler conics should help us handle these very quickly without even having to go to standard form, right? So for example, this one, as you can see, we have a square on the x, but not on the y, and we should be able to turn this into a form that's very familiar to us, right? Notice that if I solve this equation for y, I get 2x squared plus 9x minus 20 equals y. Of course, I can always write the y on this side for more familiarity, right? Because of the symmetric property, which says if a equals b, then b equals a, right? So if I do that, I notice that this is definitely going to be the equation of a parabola, right? We recognize this. There's not much work that's needed at this point. We know we've studied these in great detail. So here we can go ahead and confidently say this is a parabola. And it's definitely one of the non-degenerate conics, because we are asked to identify that as well. Okay, I brought this over for us because I wanted you to see that it does indeed satisfy this condition, which a or c, but not both, must be 0, right? And a and c, remember, are the coefficients of the square terms. So a was the coefficient of x squared, and c is the coefficient of y squared. And notice here c is 0 because there's no what? There's no y squared term. All right, so I brought in this general form for you as well, so you can see that c is the coefficient of the y squared, and here there is no y squared term, so c is in fact 0, okay? All right, so here's another equation for you to consider. See if you can figure out what kind of a conic that is before you continue watching. Okay, so as we move on, some of them will be easier to determine from the general standpoint, and some from the standard standpoint. So notice with this one, as you recall, this is very much close to this form, so we'll go ahead and show that it can easily put into that form. Notice that if we just solve for y minus 2 squared, we get -1/4 times x minus 2. which is this form right here. So we can see this is also going to be representing a parabola. And once again, it's non-degenerate. All right, so that's how we do that one. All right, here's another one. See if you can tell what that is before you continue. All right, so we've done enough of these graphs where you should recognize this is probably going to be one of these 4 types. So we won't be able to tell until we move both the square terms to the left side. Okay, so we end up with x squared over 64 plus y squared over 25 equals 1, which we recognize very simply as an ellipse. It is, of course, one with a horizontal major axis, because the a squared, which is under x squared, is the larger number. And we're right here in this form with h and k both being what? 0, right? So the center would be at 0, 0. But again, we've done plenty of graphing. This time we're just mostly interested in identifying, right? So we know that this is an ellipse, which is one of the non-degenerate conics. All right, and that's all we have to do there. All right, so this one should be very fresh in our minds, because we just did the section on hyperbolas. Of course, when there's a minus here, we get a hyperbola. This is actually going to be an interesting one. It's kind of where the fundamental rectangle is, of course, going to be a square, right? Remember, a square is just a special kind of rectangle, right, where all 4 sides have the same length. All right, so this one was very easy. It's a hyperbola. And it's definitely a non-degenerate conic, right? Let me just be lazy there. Okay, so that's that. Here's another one. It's a little bit off center, right? It's a translated hyperbola, but nevertheless, it's definitely a hyperbola. And because the positive term is the x squared term, this is going to be a left-right horizontal hyperbola, right? And definitely non-degenerate. Okay, what about this one? See if you can determine what that is before continuing. Okay, as you've probably guessed, because of that 0 there, we're going to have a degenerate conic here. And as to which one it is, well, if you just put it in standard form, you can see we end up with x minus 2 squared, divide both sides by 16. And you end up with that, right? So now you know that if we had quantity x minus h squared plus quantity y minus k squared equals r squared, that would have been a circle, right, of radius r centered at hk. Well, this is kind of, can be thought of as a circle. It's a circle of radius 0, right? Well, technically we don't like to say that, but unofficially that's kind of what it ends up being, right? So basically, when this happens, think of a circle of radius 0 as a point, right? So this is, if you were to graph this, you would graph this point in the Cartesian coordinate plane. So the result here is a point which is a degenerate conic, okay? So it's one of the degenerate variety. again, you can graph that. You just go to 1, 2, and then down 3. There it is. There is the graph of this equation. It's a single point located at 2, -3. In fact, sometimes someone may ask you to go ahead and create an equation to represent the point, say, 2, -9, right, in the Cartesian coordinate plane. You can easily do that, right? You would just go what? You would just go x minus 2 squared plus quantity y minus -9, which becomes y plus 9 squared equals 0, right? There you've just generated an equation that would have a graph as a single point and at a very specific point, this one, right? So it's very easy to custom design an equation which would represent a point in the Cartesian coordinate plane. All right, see if you can tell what that equation represents before continuing the video. All right, so we of course recognize this as a parabola. Now it's not the type of parabola that's going to be a function, because it's the x which is not squared and the y which is squared. So if you actually solve this for x, you would get x equals 4y squared minus 7/2 y. You may recognize that much more readily as a equation of a parabola. So we know it's a parabola, and it does satisfy this condition, right? Remember here we have the c, which is not 0, and a, which is 0. So again, we have a parabola. It's actually a right parabola, not an up-down parabola, right? And it would, because of the positive 4, it would open to the right, like so. Okay, and so we have a parabola, and it's a non-degenerate conic. Okay. All right, so we have one which is very much in general form. So as I have said before, it is the safest thing to do is to put this in standard form, then decide what kind of conic you're looking at. Go ahead and see if you can figure that out before you continue. All right, so remember that the way we approach these, we've done these before, so this should not be very new to you. We go ahead and put the x terms next to each other, and then we put the y, leave some space for completing the square, and then put the y terms next to each other, right? And we'll go ahead and move the constant to the other side. And now we're going to go ahead and factor a 3 here, because in order to use the completing the square trick, which is take half the coefficient of the first degree term and then square it, we need to have a coefficient of 1. So first we need to make sure that the x squared has a coefficient of 1 on the lead term, right? Minus 6x. And let me leave some space here and go ahead and factor out the 4 as well. So I get 4 times y squared plus 2y. All right, so now let's see what we need to add. So we need to take 1/2 of -6, which is -3, and we need to go ahead and square it to get 9. So we need to add a 9 here, and for the other one we have y squared plus 2y. So we have to take 1/2 of y, the coefficient of y, which is 2, that gives us 1, and then we're going to square it to get 1, right? So we need to add 1. But be careful, because we're not just adding a 9 to the left side of this equation, we're actually adding 3 times 9. So 27. So we have the negative 31 on the other side. We add 27. And here we're not just adding a 1, we're adding a 4. So to keep the balance, we have to add 4 to the other side. So we end up with 3 times x minus 3 squared plus 4 times y plus 1 squared equals, on this side we have 31 minus 31, so that's 0. Now, if we go ahead and divide both sides by 12, we can get it into a more familiar format. So we get x minus 3 squared over 4 plus y plus 1 squared over 3. 0 divided by 12 is just 0, right? So we get that, and as you can see, this you should recognize as one of the forms we've seen for the degenerate ones, which will generate a point once again. All right, so as you can see, we are in this form, and that's going to generate a point, and we should mention that it is a degenerate conic. So point, and it is a degenerate conic. Now, remember, just because we have the 4 and the 3 down here, it doesn't mean the point we're going to get is going to be something other than 3, negative 1. No, these are not going to make any difference. The only ordered pair xy which is going to satisfy this equation is still going to be the ordered pair 3, negative 1. So if you were to graph this, you would still get that single point as the graph of that particular equation. So there we have it. All right, here's another one. See if you can figure this one out before you continue. Try to put it in standard form or maybe another approach. All right, as you've probably guessed, the existence of this xy term here is going to complicate matters a bit because it's going to be difficult to put it in one of the standard forms we recognize. However, I do notice this is a trinomial that seems to be quadratic in form. I should possibly be able to factor that, see if I can get any information from doing so. So let me go ahead and try to factor this to see what happens. Okay, so if I go, I'm just going to do trial and error FOIL method, right? Maybe that, and then perhaps a 3y and a 1y. Okay, again, with experience, you get better and better at doing this. So let's see. So I want to get a positive 10. So I want this to be positive and this to be negative. So let's check it. First times first gives me first. Last times last. Pay attention to the signs. Does give me the last term. And the inner product is negative 2xy. The outer product is positive 12xy. They do combine to give me positive 10xy. So the factorization is correct. So this is one of the interesting situations that may arise when it comes to these conic sections. And notice what happens. If I try to solve this, I get either 4x minus y equals 0 or 2x plus 3y equals 0. So here, in this, on the left one, I end up with 4x equals y, which if you write as y equals 4x may be more familiar to you. And this one gives me 3x equals negative, 3y equals negative 2x. So y equals negative 2/3 x, right? So as you can see here, these possibilities that we have found give us a pair of intersecting lines. The graphs of both are, of course, simple lines, and notice that the y-intercept is 0 for both of them. So we know that they're going to meet at the origin. The more correct language would be to say the y coordinate of the y-intercept is 0, because that's what b is, you know, mx plus b. For both of them, b is 0, and of course that means the y-intercept is going to be at 0, 0 for both of them, and they meet at the origin. Now, another interesting to note is that they're not in the simple form of y equals some constant, so therefore they're both oblique lines. They're neither horizontal nor vertical. That happens because of the existence of this 10xy in the middle. This xy term is what turns them into an oblique scenario. Let's take a look at the graphs to gain some more insight. So notice it makes no difference whether you graph this form or the factored form. Here's the, you know, right now we're seeing the graph of the top form. If I turn that off and do the bottom one, it's the exact same graph. In fact, if I turn them on, they're going to overlap. Okay, so notice that it's the 0 on the other side of this equation that's turning this into a degenerate hyperbola. If I change that to even a 1 or any number other than 0, I'm going to end up getting a hyperbola. Let me show you. All right, so here I just changed the 0 to a 1 on this equation right here. Notice we ended up with a hyperbola. You can change that to any number as well. You know, it doesn't even have to be a nice 1. It could be 0.1, whatever. The smaller it is, the closer it's going to get to that degenerate case, right? So if I just do 0.1, notice that's almost a degenerate hyperbola, but not quite. And of course, the larger I make that, the further it's going to get away from being similar to the degenerate case. Again, this xy is what creates the oblique nature of the lines. If we had a simple scenario where the xy wasn't there, let's say the factorization ended up being like, for example, 4x minus, say, 3 or 4, whatever, it doesn't matter, yeah, times, say, 2x minus 5, see, equals 0. Then you would end up with, well, we want one of them to be x and the other to be y, right? So notice this time you do get intersecting lines. However, notice that this time they're going to be horizontal and vertical lines, right? So whenever the xy term is absent, you end up with just horizontal and vertical intersecting lines. When the xy is present, when you do the factorization, which means we're going to have at least one y here or one x on this side, then we end up with the oblique scenario that you see. In fact, if you simply, let me turn all these off. If you simply just graph, say, x times y equals 1, you can see we've graphed these before in our sections that covered graphing of equations, and these always ended up giving us an interesting case of this oblique kind of hyperbola, these rotated hyperbolas. All right, so here we get intersecting lines. It's also known as a degenerate hyperbola, and it's definitely a degenerate kind of conic. All right, here's another one for you to try. Go ahead and see if you can figure out what kind of a figure we have here, or non-figure if it's not possible. So give it a shot, see what you do before you continue watching. Okay, so we're going to put this in standard form. I'm going to leave some space. And I'm going to move the 45 to the other side so it becomes negative 45. All right, so let's go ahead and factor out the 5. That gives us x squared minus 4x, and then plus 6 times y squared plus 4y, and then equals negative 45. So I noticed that for the first trinomial here, I need to take half the coefficient of x, which is negative 4, that gives me negative 2, and square it to get 4. So I get plus 4 within the parentheses. For the other one, I need to take half of 2, which is 2, and square it to get 4. So I need to add 4. So now we have 5 times x minus 2 squared. But let's be consistent. Before we move to that step, let's realize here for this one we added a 20. For this one we added a 24. So plus 20 plus 24. Okay, just to make sure we don't forget that. So 5 times quantity x minus 2 squared plus 6 times quantity y plus 2 squared equals negative 1, because 44 minus 45 is negative 1. Now, I could stop right there and tell you that this is not going to have a graph, but in case you want to go to one of the standard forms, let me show you which form I'm talking about. Here they are. Remember, and either one of these two forms would end up giving you no graph because of the negative situation. So if you want to get to one of those forms, you could, but I'll tell you, you don't need to, because this is positive times a positive number, and then this is positive times a positive, so their sum should not be negative. So we could stop right there and say no graph, but if you really wanted to go to one of these forms, you could divide both sides by the LCM of those two numbers, which is 30, and you would end up with quantity x minus 2 squared over 6, right? Remember, we're dividing by 30, so they're going to cross cancel and give you 6 down below, plus y plus 2 squared over 5 is equal to negative 1 over 30. Remember, we're dividing both sides by 30. So now you can see we're definitely in this form, right? So we know this is not going to end up giving us a graph, because there's no ordered pair xy we can find that is ever going to satisfy this equation. So how can we get a graph, right? That's why. All right. Now notice this is precisely why I told you the safest thing to do is to go to standard form, because if you were just going to rely on this method that we discussed with respect to the general form, here we do indeed have a and c, which are 5 and 6. They're non-zero and they're not equal. So that's why we said it may be a non-circular ellipse, because this scenario may happen, in which case it's what? It's none of the above. So that's why it is never good just to rely on these tests that we have in general form. They only give us possibilities. For certainty, you always want to go to standard form. All right, here's another one. See if you can figure this one out before you continue. Okay, so I notice this is pretty simple to put into one of the standard forms, and that would be what? X squared plus y squared equals negative 64. Once again, we have the sum of two squares giving us a negative number, so we know this is going to have no graph. Okay. And why is that? That's because you're never going to find an ordered pair xy that's going to satisfy this equation. So how can you graph points that don't exist, right? That's why. Try this one before you continue. All right, so this one looks more promising in my opinion because I can quickly move the y squared to the left, so I get this, right? And if I want to go to standard form, I'll divide both sides by 9. So we can see here we have a hyperbola, okay? It would be very easy to graph as well, right? You would just make your xy axis. Here's my attempt. You would just go, notice that the center is 0, 0 because there's no h or k to worry about. Well, they're there, but they're not visible because they're zeros, right? So we go 3 to the right from the center, 3 to the left, and then we go up 3 and down 3. We form our fundamental rectangle. And then we draw our asymptotes. All right, so because the x squared is the positive term, I know that the vertices are going to be at these points on the fundamental rectangle. And then I quickly draw my hyperbola like that. Like that. Of course, you know, it looks much nicer than that, but there you go. There's the general idea. All right, so notice the interesting thing is it would have made no difference if I were trying to graph this at first. I would have gone through the exact same steps until the very last step where I decide where the hyperbola is going to exist, right? Now, if I were graphing this, of course, I would have done this. That would have been the only difference. That would have been the graph of this particular equation here. All right, so we do have a hyperbola. And it's definitely a non-degenerate conic. All right, how about this one? What do you think this one is? Okay, I think I heard you say it's a line. You're right. Of course, you know, as a conic, as a linear equation in itself, it's very respectable. But you know, since we're looking at it as a conic, of course, we consider that to be a degenerate conic section. So it is definitely a line. If I just write it like this, there you go. You recognize it now, right? All right, so this one would be a line, and it is a degenerate conic. Okay, let's go ahead and go on. All right, let's just do one more for the road, and this is it. Go ahead and figure this out, and we'll wrap it up. Okay, before I actually do anything, I can't ignore the fact that I can see 4 goes into every one of these, right? So before I do anything, I'm just going to go ahead and divide both sides by 4. I mean, we've done similar problems. The only reason I gave you this one because I wanted you to notice that when that opportunity exists, you should take it, okay, to simplify matters. So let's go ahead and divide both sides by 4, so we end up with x squared plus 4y squared minus 4x minus 24y plus 24 equals 0, because 0 divided by 4 is just 0 anyway. So we have x squared minus 4x, leave some space, plus 4y squared minus 24y, leave some space, equals negative 24. So x squared minus 4x, take 1/2 of -4, which is -2, and square it to get 4. So plus 4, and we'll go ahead and add it right away, not to forget, and then plus 4 times y squared minus 6y plus take 1/2 of -6, which is -3, and square it to get 9. But remember, you're not just adding 9, you're adding a 4 times 9, which is 36, so plus 36. So we have quantity x minus 2 squared plus 4 times quantity y minus 3 squared equals -24 plus 4 is -20 plus 36 is 16, right? Now to really get it into standard form, we know it's an ellipse, but let's divide both sides by 16, so we get x minus 2 squared over 16 plus quantity y minus 3 squared over 4 equals 1, okay? And yeah, we can definitely see it's an ellipse. All right, so that should do it for this lecture. I hope you know how to identify most of these now, and that should take care of this lecture. Have a good day, and we'll see you at the next one.